Hi everyone, in this video we are going to solve this example. So what is the function we have? 1 upon z minus 1 square, z minus 2 cube. We have to prove that here z is equal to 1 is a pole of order 2 and z is equal to 2 is a pole of order 3. This thing we have to prove with the help of definition of pole. Okay, so let me write the given function first. We have, what is the function? Okay, just a minute. We have, our function is 1 upon z minus 1 square, z minus 2 cube. Okay. So first of all we will find the singularities. Singularities, that means a point where the function is not analytic. So in this case what we do, we find the points where the denominator is 0. You can easily see, if I put z is equal to 1, denominator will be 0. So z is equal to 1 is a singular point. Similarly, if I put z is equal to 2 here, again denominator will be 0. So z is equal to 2 is also a singular point. So let me clearly mention here, z is equal to 1 and z is equal to 2 are singular points. See, but what we have to prove? We have to prove that these are poles. So pole is one special type of singularity where in a Lorentz expansion, principal part has a finite number of terms. In previous video we have already seen, right? So here what will I do? I have to find the Lorentz expansion of f of z at z is equal to 1. In using that we will prove that it's a pole of order 2. And after that we will find the Lorentz expansion of f of z about z is equal to 2, and we will prove that z is equal to 2 is a pole of order 3. So let us focus on z is equal to 1 first. Okay, let me mention now, we will prove that z is equal to 1 is a pole of order 2. Okay, so let us find the Lorentz expansion. So f of z, what is our f of z? 1 upon z minus 1 square, right? Z minus 2 cube. So this is a given function. See, we have to find Lorentz expansion of f of z at z is equal to 1. That means we want this bracket z minus 1 everywhere. Okay, everywhere we want in a series expansion. So z minus 1 already we have in the first bracket. So we have to adjust z minus 1 in the second bracket. So let us do that. I will do it here. Okay. See. So f of z is equal to 1 upon z minus 1 square into this bracket I am going to take. Z minus 1 we want. So that's why I am expressing it as z minus 1 cube. You know that minus 2 means minus 1. Okay, so we want minus 1, so that's why I express in that way. Let us move further. After that, see, there are two basic series which we frequently use. Okay, let me mention 1 upon 1 minus z and 1 upon 1 plus z. So when we want Lorentz expansion, most of the times we use this series. See, its expansion is 1 plus z square plus z cube and so on, and having a same expansion, just alternating minus plus signs. Okay, so out of this two, one series I am trying to use here. Okay, but see, you can easily see at the bottom the first term is 1, so there also I will try to bring 1. This is equal to 1 upon z minus 1 square into 1 upon, what will I do? I will take minus sign common. Cube is already there, getting? So minus sign I am taking common. So this 1 will be plus. That's why I am writing first. And this z minus 1, this is term I am considering, sign will get changed. So minus z minus 1 bracket. Have you understood what I have done? Z minus 1 I have treated as one term and 1 is there. So by taking minus sign common, it will be plus and this term will have a minus sign. But see, minus cube, that means minus will appear 3 times, minus into minus again minus. So that's why it will be 1 upon z minus 1 square into, that minus sign will come outside, I am writing it numerator, 1 minus z minus 1 cube. So tell me, can I use this series 1 upon 1 minus z, getting 1 upon 1 minus, at a place of z we have z minus 1. Can I use this series? No, because here the bracket has power 3 and there is no any power, okay, to this 1 minus z. So this series we cannot use here, but see, let us see how to bring a new series, okay, with the help of this one. Just a minute. Before that, I will take minus sign here. So minus 1 upon z minus 1 square into 1 upon 1 minus z minus 1 cube. Okay. So what is the basic series we have? Let me write. We have 1 upon 1 minus z, 1 plus z square plus z cube plus z raised to 4 plus z raised to 5 plus and so on. So we are familiar with this series. Simply we want a bracket cube. No problem, we will bring it, okay. There is one condition, mod z less than 1, I should mention here. There is no more space to write, make a screenshot of it, then I will go further. So let us continue, okay. See, actually we have 1 upon 1 minus z, but we want bracket cube. What will I do? I will take derivative of both sides. Let us see what will happen if I take derivative. You know derivative of 1 by z? Derivative of 1 by z is minus 1 upon z square. So the same formula I am using here, okay, here. So what will happen? If I take derivative, it will be minus 1 upon 1 minus z bracket square. But see, by chain rule, we are supposed to take derivative of this 1 minus z again, which will be minus 1. So into minus 1 by chain rule. Let us take derivative of right hand side. Derivative of 1, 0. Derivative of z, 1. Derivative of z square, 2z. Derivative of z cube, 3z square. Derivative of z raised to 4, 4z cube. Derivative of z raised to 5, 5z raised to 4. That's enough. Plus and so on. Getting? So minus minus plus 1 upon 1 minus z square is equal to 1 plus 2z, 3z square, 4z cube, 5z raised to 4 plus and so on. But see what we want bracket cube. We have bracket square, it means we need to take derivative again. Let us take one more derivative of both sides and let us see what will happen. Okay. So its derivative will be, okay, let me tell you the formula which I am using here. Derivative of 1 by z square is minus 2 by z cube. So how did I get this formula? The basic formula is actually z raised to n, derivative of z raised to n z raised to n minus 1. This is a basic formula which I am using here. What we do, we shift this z square to the numerator, it will be z raised to minus 2. We are applying the same formula, take the power first and reduce it by 1. By applying the same formula, minus 2 z raised to minus 3 we will get, and by shifting at denominator we get this formula, okay. So this is a basic formula behind all this. Same formula I am going to use here, okay, same formula. This formula I am going to use, at a place of z we have 1 minus z. So it will be minus 2 upon 1 minus z cube. But again by chain rule, we have to take derivative of this bracket which is minus 1. Okay, so let me remove this part. Now it's time to take derivative of right hand side. What is derivative of 1? 0. 2 is constant. Derivative of z, 1. So 1 into 2, 2. 3 is constant. Derivative of z square, 2z. Into this 3, 6z. 4 is constant. Derivative of z cube, 3z square. That 3 into 4, 12z square. Z raised to 4, its derivative is 4z cube into this 5. 4 into 5, 20 z cube plus and so on. Okay. See this minus minus plus. Did you notice one thing? All these terms are divisible by 2. Okay. Let us divide all these terms by 2. So it will be 1 upon 1 minus z cube is equal to 1 plus 3z. I am dividing all these terms by 2. 6z square 10z cube plus and so on. Getting? Yes. So finally I got the expansion of that bracket cube. Okay, I got the expansion. So I am going to use this series here. But at a place of z, we have z minus 1. This is the only difference. Let us use. Then or therefore you can write, therefore f of z is equal to, what we have, the first term is minus 1 upon z minus 1 square into, I am going to use this series 1 plus 3, z at a place of z, what we have, z minus 1, z minus 1. Let me remove this part so we will have some more space to write. Okay. After that, plus 6z minus 1 square plus 10z minus 1 cube plus and so on. Okay, so this is the series we got. See, we want some more space to write. Let me remove that part. See, now what will I do? I will multiply each term by this minus 1 by z minus 1 square. Let us see what will happen. 1 into anything you will get same. Okay. Next, I am multiplying the second term by this one. So, z minus 1, one bracket will get cancelled and we will have minus 3 upon z minus 1. I am multiplying second term by this bracket. So, z minus 1 square will get cancelled and we will have minus 6, right, minus 6. Let us multiply fourth term by this one. So, we will get, see, my z minus 1 square will get cancelled and minus 10 z minus 1. Am I right? Yes, cancel. Yes, we will get this one and so on and so on and so on, plus and so on. See, here, this is the analytic part. This is analytic part of this Lorentz expansion, since that bracket appears at numerator, and this is a principal part. This is a principal part of this Lorentz expansion because that bracket appears at denominator. So tell me, how many terms are there in a principal part? Only 2 terms are there. That means principal part having finite number of terms. So therefore z is equal to 1 is a pole. Yes, so in this way we proved. So therefore z is equal to 1 is a pole. Okay, so we got the reason why how we can say it is a pole. And see, what is the highest power of that bracket in denominator? 2. So that's why it's a pole of order 2. Pole of order 2. So in this way we proved that z is equal to 1 is a pole of order 2. Okay, after that the second part is also there. We have to prove that z is equal to 2, that is also pole, and it is a pole of order 3. So the same thing I am going to do, just make a screenshot of it, then I will go further. Okay, so let me clearly mention here. Now we will prove. Now we will prove that z is equal to 2 is a pole of order 3. This thing we have to prove. Z is equal to is a pole of order 3. It means we have to find Lorentz expansion of this function at z is equal to 2. So let me mention f of z plus first z minus 1 square, z minus 2 cube. So what did I say? We have to find Lorentz expansion at z is equal to 2. It means in that series we should have this bracket everywhere, z minus 2, z minus 2, z minus 2, and its powers obviously. Z minus 2, this bracket already we have, so we need to adjust that bracket here. Let us see what will happen. Let us see how we can do this one. So it's quite easy job getting z minus 2 now. So what will I do? Minus 1 we have already we have. So z minus 2 plus 1, that's it, finish. Z minus 2 plus 1, minus 2 plus 1, minus 1. Same term, same bracket I have written in a different way. Since we want z minus 2 everywhere, this is my 2, okay. See, after that we have to use the expansion of that series. What will I do? I will write this bracket first. 1 upon z minus 2 cube into 1 upon, see this bracket I am writing here, bracket square. 1 I will write first, 1 z minus 2. Okay, so why I am writing 1 first? Since we are familiar with this series 1 upon 1 plus z, that is 1 minus z plus z square minus z cube and so on, getting? So here also we have 1 first, so that's why I wrote 1 here first. Okay, so tell me, can I use this series expansion here? What do you think? No, it's not possible, because we have a bracket square here, right? We have a bracket square and there is no any bracket square. But no need to worry, getting? I will use the same technique which I use for the first part. Okay, I am going to use the same technique. So yes, let me write. We have, I will write the series which we have. We have 1 upon 1 plus z is 1 minus z plus z square minus z cube plus z raised to 4 minus, no, here minus z raised to 5 and so on. Okay, see, we want a bracket square, so that's why what will I do? I will take a derivative of both sides. So you know derivative of 1 by z. What is derivative of 1 by z? Tell me. We have already seen in first part. It is minus 1 by z square. So the same formula I will use. So therefore minus 1 upon 1 plus z square. But by chain rule, again derivative of this bracket, but fortunately its derivative is 1, so that's why no need to write anything. We can go further. So now it's time to take derivative of right hand side also. Just tell me one by one. Derivative of 1, 0. Derivative of z, 1, it has a minus sign, plus derivative of z square, 2z, derivative of z cube, 3z square, derivative of z raised to 4, 4z cube, its derivative 5z raised to 4 plus and so on. See, to remove this minus sign, I will multiply both sides by minus 1. So we'll have 1 upon 1 plus z square is equal to 1 minus, all sign will get changed, no, if you multiply by minus 1. Okay, and so on. So now it's time to use this series. Okay, the obvious condition is mod z less than 1 here. Okay, therefore, so let me use this series expansion here. What is the difference? At a place of z we have z minus 2. This is the only difference, remaining part is same. So in series expansion also we should replace z by z minus 2 everywhere. Therefore f of z, this 1 upon what we have, z minus 2 cube, into, I am using this expansion, 1 minus 2 z minus 2 plus 3 z minus 2 square minus 4 z minus 2 cube plus 5 z minus 2 raised to 4 and so on, and condition is mod z minus 2 less than 1 obviously. So now what will I do? I will multiply each term of this bracket by this 1 upon z minus 2 cube. Okay, I am going to do that. Just make a screenshot of it first, then I will go further. So now let us see. Okay, f of z is equal to f of z. I am multiplying each term by this bracket 1 upon z minus 2 cube. If you multiply anything by 1, you will get same. If you take the product of this one and this one, z minus 2, one bracket will get cancelled and you will have minus 2 upon z minus 2 square. If you take product of these two brackets, bracket square will get cancelled and 3 upon z minus 2, am I right? If you take product of these two brackets, here also we have z minus 2 cube, here also, so that bracket cube will get cancelled and you will have simply minus 4. Product of these two terms, bracket cube will get cancelled and you will have 5 z minus 2 and so on. Okay, you can easily see all these terms, in all these terms z minus 2 appears at numerator, so this is the analytic part and this is the principal part of Lorentz expansion. So how many terms are there in the principal part? 3. Okay, so principal part is having finite number of terms, so that's why it's a pole, I can declare. Therefore z is equal to 2 is a pole. So what is the highest power of that bracket at denominator? 3. So highest power is 3. So that's why it's a pole of order 3. Pole of order 3. So in this way we proved that z is equal to 1 is a pole of order 2 and z is equal to 2 is a pole of order 3. In this way we have completed the solution of this example. Just make a screenshot of it, then we will stop. Thank you. See you in next video.